Well, howdy there, Internet people. It's Professor Leach again, and today we're going to continue talking about integration by substitution. A couple days ago, we started looking at integration by substitution as an anti-chain rule, and just started kind of guessing by looking at the function where it came from with respect to the chain rule. And then yesterday we started putting a formal process, in this formal process, on the technique of integration by substitution. This one I spend extra time on because this is a very important technique. It is really important to be able to change your variables, not just for integration by substitution. That's just the convenient thing that we get to use it for now. It's an important thing to be able to change your variables. If we don't like the way that a problem is written, if we don't like this variable, it's complicating things, we look for a way to simplify the variable, look for a simpler variable that really gets at what's going on in the problem, and then use that information to integrate. The namesake substitution, it happens right here. We're substituting all of our x variables for w variables. All the x's must become w, so here are the two substitutions that we're making. We're not just trading our g of x for w, we're also trading our dx for dw. So we make these substitutions to trade our integral in x for an integral in w. Then we integrate the integral in w and then take it back to x. So we have an integral in x. The structure looks like this. There's an integral in x. We substitute that for an integral in w. And so that's where we do our substitution. The integral in w is going to be one that's easier to integrate, so that's when we actually integrate. But the result here is going to be an antiderivative in w. So we have to resubstitute back. We have to unsubstitute back to our antiderivative in x. So we're trading from one set of variables to the other. And this is a structure that happens a lot in math. You switch to a different set of variables, do the thing that you want to do in terms of that set of variables, and then go back to your original variables. And that's how we bridge this gap here, use a different set of variables. So this first line is us trading our variables in x for our variables in w. All the x's have to become w's for this to go. Then we can integrate, that's this step down here from, that's why the plus c shows up, because our integral dw says here's f of w plus c. And then we just have to go back to our original variable, f of g of x. The important thing that we need to be able to do to make this process go is identify inside functions and outside functions. What's been plugged into the outside function? Because that'll tell us what function we're actually integrating and what's just there to changing the insides. So we really need to be able to read what's going on in the function. We need to be able to read what's going on in the function. We need to be able to read what's going on in the integrand. That's the function we're integrating. We need to be able to read what's going on in that function so that we can apply our technique. Most of the time in a math class, we are spending learning how to read the symbols that are being put in front of us. That's a lot of what we spend time doing, reading what's going on. The difficulty that we have is that we try to read it in the same way that we read everything else. For example, notice that my writing here is fairly messy, but it's not hard to determine what's being said, first of all, because I said it out loud. And second of all, your brain can do a lot of the work figuring out what the words are based on the context, based on, you're just doing kind of that predictive text that your phone is trying to do. It's like, oh, I know what's coming next. I dropped in a new word, so maybe that one comes out, I don't know. Maybe your phone is going to shrug at that. But for the most part, when you read the words, you're not actually reading this word function as F-U-N-C-T-I-O-N. You're not processing every single one of those letters and trying to put it together into a word. And when I say things like this, I'm speaking from a neurotypical standpoint. From a neurotypical standpoint, we don't look at this word as a collection of letters that we have to assemble and then decipher. We just kind of see the whole thing and just kind of gloss over it. We don't actually read what's going on. That's how we can read past spelling errors. As much as emphasis as we like to put on things like spelling, we can, for the most part, read right past spelling errors. That's how good we are at deciphering the symbols that are in front of us. That ability becomes very limited when we start dealing with math, partially because math is a much more precise written language than, I'm just using this one, English. So we don't get to use the same kind of processing when we're reading math than when we're reading English or our native language, the one that we've always been reading. Because it's new, for one thing, and it's very precise for another. So there are a lot of things that we can say that we don't actually read correctly. And it requires that we work from a common base of knowledge. That's kind of how this whole language thing works. But if I say something like 3 times x plus 5 squared, we all think that we're thinking of the same phrase. But if you told me to write 3 times x plus 5 squared, I am probably not going to write what you think you are reading. So math it works differently, and we have to train ourselves separately to process this kind of information, this kind of written language. With that in mind, let's look at an example of a function and decide what's inside and what's outside. And let's decide, since this is a substitution exercise, let's figure out what needs to be there to make substitution go. So on these examples, identify an inside and outside. I want that there. What's inside? What's the outside function? That's the thing that we're actually going to be integrating in the examples that I write. And then what else do we need to make substitution go? Three things that we want to identify. I'm going to write down some functions, and I want you to identify what's the inside function, what's the outside function, and what derivative of the inside will we need to make substitution happen. So for example, let's suppose that I had a function I'm going to use one that we looked at yesterday. Let's suppose I have the sine of x squared, and then leave a space, dx. I'm leaving this space because that's the inside that we need to make substitution go. Also note that I just wrote sine x squared. That's not a very good way to say that. It's the sine of the square of x. That's a little more clear, even though verbally it's not. So I'm leaving space for the derivative of the inside. So if we were going to integrate, if we wanted to integrate sine of x squared, what would you identify as the inside function? What happens to the x first? We're going to make a substitution, so w is going to be the inside function. (2x) is not the question I'm asking yet. X squared is the substitution that we would make. That's the inside. What function is the substitution in? What is the f prime function that we're going to be integrating? What's the outside function? Sine. And so if we want to make this substitution w equals x squared, what are we going to need out here to be the dw? So what's the derivative of the inside that we would need to see out here to make this happen? So dw needs to be some multiple of 2x. And then we multiply both sides by the dx just for formality's sake. So to make this a substitution problem, if I'm looking at sine of x squared, the x squared is inside the sine function. If we're having trouble reading that, think about what the order of operations tells us to do. The order of operations says to do x squared first and then take the sine of what you get. So take the x and square it first, then calculate the sine. Once we claim we want to do x squared, dw is going to be a multiple of 2x. So I need some x over here. It could be just x by itself. It could be a 2x, which is exactly what we need. It could be 10x or 1/3 of x. All we need is some constant times x. K can be any constant it wants. Any real constant. Don't try to be sneaky on me. So we want to be able to read what's happening in the function. In the order of operations, x is getting squared, then we do the sine of it. You can probably see exactly what the next example is going to be, although it's going to have to be on the next page since I didn't really give myself enough space. So let's do another exercise, another example, where I'm going to integrate. Now it's going to look differently. Now I'm going to write the sine, and the square goes here of x. I still want to know what's going to be the derivative of the inside to make the substitution go. There's still going to need to be a dx because that's just punctuation. Think of the dx as punctuation. If you don't think it's important, first of all, you don't have a basis for making that decision. And second of all, if you don't think the punctuation is important, next time you turn in an English paper, leave off all the periods and see how it goes. All right, so we can do a substitution here, but we're going to need something, just like we needed the x before. So there's the same 3 questions. What's the inside function? And what are we plugging it into? So what if I wanted to calculate sine squared of x, what do we do first? What's the order of operations in this expression? Substituting x for w would just be rewriting the x's as w's. That will never do anything. What does sine squared of x mean? Think about what we mean when we write sine squared x. We mean sine of x squared. We didn't want to type that out because there's so many parentheses and we don't like typing things with lots of parentheses in it, but we need to get used to it. If you can't type your expressions with parentheses, you really can't read. And you're just kind of faking it through your algebra. So now that I've written this expression as sine of x all squared, because that's what we mean when we say sine squared x, what's the first thing that happens to the x? What do we do first to the x in this expression? We want to calculate sine squared of 30. What do we have to do first? Do we square the 30? That couldn't be it, because that's, if we want to square the 30 first, this is how we write it. When we see sine squared x, we mean the square of the sine of x. In the previous example, we wrote sine of x squared, which means the sine of the square of x. So what I've got here is the same two functions, but I've composed them in the other order. So our substitution here, w is equal to the sine of x. And what sine of x has been plugged into is an x squared function. I'm just going to write parentheses. So if w is equal to sine of x, then the dw that we need, the derivative of sine is cosine x, and then the dx just goes with that. We multiply both sides by the dx. So, and we need a multiple of this. So we need k times the cosine of x, and k is still any constant. So the important thing to be able to do is to look at an expression and read what that expression is asking you to do. In the first example, we had the we had the sine of the square of x. And in the second example, we had the square of the sine of x. So when we write sine of x squared, the order of operations says first do the x squared, and then take the sine of what you get. So I'd read this expression as the sine of the square of x. The second expression said sine squared x, and we know this to mean the square of the sine of x. So the order of operations in this expression, is first we do the sine of x, and second we do the square. And so to read this expression, we would say this is the square of the sine of x. So if we want to read it so that people understand exactly what we're talking about, if we want to speak precisely, I would speak this symbol as saying the sine of the square of x. And I would speak this symbol as the square of the sine of x. Because then I'm being clear. Usually when we say things like, the reason that we do this is that this is the two orders that we could put these two operations in. So when we say sine x squared, we mean the sine of the square of x. And so that's the reason that we stick the 2 in here. That's the reason that we decided to stick the 2 in here, because then it says, oh, let's write it this way. Sine squared x means do the sine first, then square it. Whereas if we say sine x squared, we square first and then sine it. Any questions? The reason that I really want to, that I emphasize this so much, and I say things like this over and over again, is that we are really lazy in how we speak mathematics to one another. Usually we just SPELL space THE space FUNCTIONS that we're trying to communicate. Usually we just start spelling things at each other. And it sounds terrible, and we don't want to do that. So we try to read these things, but we use our practice, the practices that we learned in, we try to use the practices that we learned when we were speaking, for example, English, and we just kind of like read the letters in order. And we just can't do that in math. That's just not how we write things. We need to write things differently. I write 2x when I mean x plus x. I mean, I write x squared when I mean x times x. In both cases, there's 2 x's. With addition, I put the 2 in front as a coefficient on the left. With the multiplication, x times x, I put the 2 on the right as an exponent. So it's important to be able to read what's going on. Any questions?
Professor, will we be covering integration by parts next week?
Yeah.
Okay, great.
That's a good video. I've never seen one that's a video on how to read calculus out loud, but that's an important thing to be able to do. For the most parts, we don't even read algebra out loud. So I want you all to know, first of all, that when I make fun of your lack of algebra skills, I'm just having a little fun. But I want you to know that I don't care what grade you got in algebra. There are probably some pretty big gaps in your algebra skills, especially when it comes to reading algebra. So, for example, a fun exercise to do. Now, if you've been in my class before, you've probably seen me do this trick, but I'm going to write down an expression, and I want you to read it back to me in such a way that I will write the same expression. So, speak this expression without spelling it. Now, before you go into this, you should see exactly what's going on. Whatever you type, unless you type exactly what will make me write this expression, I'm going to be deliberately getting it wrong, unless you force me to write exactly the right thing. So take a minute and take a look at this expression. This is a fun Friday activity. So I'm going to write an expression. Make me write that without spelling it. I'll give you a minute to work on that. I need the Jeopardy theme. I don't have the Jeopardy theme.
Can we see the numbers too or no?
I'm sorry, what was that?
You say speak this expression without spelling it, right? So
yeah, you can either say it out loud, take a minute, think about it, try saying it out loud, or you can try typing it in the chat in a sentence. Excellent. People trying to use the word quantity. When you use the word quantity, when you're speaking an expression, you're just trying to say parentheses, so you're spelling it. So let me write this one. 3 times the quantity of x minus 5 squared. So 3 times the quantity of x minus 5 squared. Oh, dang, that's not what I wanted to write. I like that. I like the pronunciation guide on x. 3 times the quantity of x minus 5 squared. No, see, x minus 5 squared. 3 times the difference of the square of x minus 5. That's good. I like this reverse type of language, but 3 times the difference of the square of x and 5. That's not quite what I wanted either, but that was close. 3 times the difference that's the key right there. 3 times x minus 5, 3 times parenthesis x minus 5, close parentheses, squared. That's just spelling it. I want you to do it without spelling it. How would you speak that in words? Not just type it out, but speak it in words. 3 times the square of the difference of x. Instead of saying x minus 5, you can say the difference of x and 5. But that will do it. 3 times the square of the difference of x and 5. X minus 5 squared multiplied by 3. X minus 5 squared multiplied by 3. That's not what I wanted. That won't do it either. 3 multiplied by the exponent of x minus 5 to the second. No, that won't do it. Because you're still what's going on there is 5 to the second. So this is the good one. 3 times the square of the difference of x and 5. Here is some proper speaking going on. That's awesome. Usually my calc classes do not speak this correctly to me. So that's like dope that you guys got that. Awesome, well done. And you know that I'm being deliberately obstinate in getting this wrong because this is a very precise language and we should learn to speak it precisely, even though we just like let a lot of this stuff go a lot of the time. So one quick thing I want to point out before we adjourn for the week. Notice what the order of operations is on this expression. What's the first thing that happens to the x in this expression? If I wanted to evaluate this for x equals 10 or some other number, what's the first thing it would do to plug in the number here? Not 10, because that's twice a 5. So I want to plug in 12 into this expression. What's the first thing that happens to the x? First thing is you subtract 5. I'm going to do shorthand, subtract 5. After we subtract 5, what do we do? After we've figured out this part inside, what's the next thing that happened? Then we square it, so I'm going to raise it to the second. Oops, I don't write a. What the heck? I never write a. I'm just kidding. I'll write a at the end of the semester for a lot of these. And what's the third thing that happens? Once your check's clear, I'm just kidding. I can't be bought. If I could be bought, if I cared about money, I wouldn't be in this profession, right? Look at the order of operations that happened in this expression. First is the -5, second is the squaring, and third, we multiplied by 3. And look how we correctly speak this expression. 3 times the square of the difference of x and 5. We just speak it in that order. You speak it in that order, and you can't get it wrong. You can only be clear. All the other ways, you're putting the operations too close to the things that you were wanting to say. This was 3 times the difference of x and 5 squared. So when you say 5 squared, there's nothing that says you want the square of the difference of x and 5. Because you just said 5 squared, and I'd be just like, oh, why don't you just say 25? And you're like, well, because that's not what I meant. But then the computer would be like, oh, but that's what you said. As a human, I would probably drop a parenthesis after the 5. But if I'm playing computer, I'd be like, oh, that is not what you said. You said 5 squared.
Professor?
Yeah.
The way you number, I mean, you listed those steps. Is that also like a good strategy for finding the inverse of a function as well? Like,
yes. Now that it's come up, this is a good way for solving equations and finding an inverse of a function. That's kind of cheating, but because no, it's not cheating to do it this way. That's cheating for me to like list 2 things at the same time when you're just doing one thing. Finding an inverse when you have an equation with just one instance of the variable, solving an equation, finding an inverse, same kind of thing. But what would the inverse function do? We'd find the inverse operations in reverse order. So we would divide by 3, then we would square roots, and then we would add 5. So the inverse. So that's an awesome question. Thank you for asking it. F inverse of x. First, we would take the x, we would divide by the 3, then we would take the square roots, and then we would add 5, making sure that we didn't add 5 in the square root. And then what do we have here? First thing that happens to the x is it's divided by 3. Second thing is it's the square roots. And then the third thing is we add 5. So here's the inverse. And then they just go around in circles. If we want to be pedantic, which we always do, but not too much, when we square things, we should recognize that this is not quite invertible because it ends up with a plus or minus. There's 2 things that we came from once we squared something. We've lost some information. So, but yes, if you wanted to find the inverse or you wanted to solve an equation, these are the things you would do to solve the equation. If I said this is all equal to 10, we would divide by 3, take the square root, and then add 5. Any questions? Ooh, I didn't write down the sentences that you had for these expressions that were incorrect. So this is a useful thing to do because this is us not just looking at an expression and pretending that we know. This is taking something that we take for granted. This is something that we take for granted and explicitly outlining how we come to those conclusions. I do the same thing in my algebra class. In my algebra class, it's week 3, and I am still talking about how addition, multiplication, and exponents work. It's also relevant to our interests here in calculus because we have to know what the inside function is. And we have to be familiar with these strange conventions that we've come up with for writing things in different orders. This is specifically why I picked sine squared and sine of x squared. Also specifically because I don't know what the antiderivative of sine squared x is. We need integration by parts for that, or trig identities, which is the real answer. It's always trig identities with trig functions. But we have to identify the order of things, the order of go for these operations, so we can identify what's the inside function and what are we actually integrating. Integrating sine of x squared, what we're actually integrating when there's an x out here, what we're actually integrating is the sine function. With sine squared x with a cosine x attached, what we're actually integrating is a squared function. Any questions? We're just trying to learn how to read, but we're trying to learn how to read math. And that's the complicated thing. Fractional exponents. Yeah, I should have just written this as x over 3 to the 1/2 power. Oh no, I couldn't write that way. I'd have to say the 1/2 power of the quotient of x and 3. What is this, a school for ants? Yeah. All right, it's going to be weird, the things that I say, because I'll respond to something in the chat, but the chat is not actually available on the YouTube video. So people are like, oh, what is he on about? It's especially going to be problematic if you didn't see Zoolander. So Most of my references are going to be towards movies that you have not seen. So there's that problem as well. Any questions about reading expressions? Identify your inside function and then think about what do you need to be the DW to make the substitution go. So if we're looking at, oh, it's right up, there's one right up here. If we have the integral of, there it is, sine squared x, and this cosine of x is not there, this is not a substitution problem, because we can't say w equals sine x, because if we want to make that substitution, this dw, we need a cosine x to be the dw. And I can't do that without the cosine x. I can't do substitution without the sine x. I'd have to do something else. Similarly, on this problem, if we want to integrate sine of x squared, if this x is not here, substitution is not the way. We can't integrate this by substitution because there's no x to be the dw. I cannot say that w is x squared without also saying that dw is x times dx. All the x's must be w, and that includes the dx. So I guess really if it looks like this. If I just asked you to integrate sine of x squared dx, you should be like, oh, dude, you need an x there to make this substitution go. Any questions? Remember, the goal is not to find the antiderivative of sine of x squared. That's just the tool that we're using to get this idea of substitution across. Because if the actual end result is to try to find the antiderivative of sine of the, which one did I say? Of the sine of the square of x, this is the technique that we will use. For those of you watching on the video later on, I just put a link to Wolfram Alpha in the chat. If the goal is to find the antiderivative, we'll use a machine to do it. If the goal is to do something quickly, get a machine to do it. It'll be quicker and more accurate. If the goal is to learn something, leave the machines out of it. Any questions? I am the machine. That also makes me think of Bartholomew.
Where's that one from?
There's this guy on TikTok. He makes a very dramatic child.
Okay.
Mother, I have injured myself. That kind of thing.
Oh, God.
All right. So, all right, that's it for today. That's very enlightening. I always love it when substitution comes up because I get to talk about your lack of algebra skills. I'm not really making fun of you. I'm not trying to be mean. I just want to point out something. So, hey, how do we read this stuff? And then you're like realizing, wow, I actually struggle with that. This order of operations business. And it comes down to this. One last thing. It comes down to this. The reason that we'll struggle with saying things like this is that we don't learn how to properly read things. We learn shortcuts. Everything, I mean, you think clickbait articles, headlines are a thing now. That's pretty much how we've done math for like the last century. It's 8 simple tricks to make you crush your next algebra test. And we did things like PEMDAS. And PEMDAS, I've said it before, I'll say it again, I'll say it to the day I die. PEMDAS, I gotta spell it though. PEMDAS is trash. PEMDAS is the reason that you can't read. I'll say it. PEMDAS is the reason that you can't read. PEMDAS is wrong, not because it'll give you wrong answers. PEMDAS is morally wrong because it treats you like a machine that we're trying to program. And you are a human child, except for you, robot. I see you coming. Any questions? Anyway, it's just a thought. Y'all have a good day.